Hello everyone, once again it's a pleasure to welcome you all to this course on inferential discrete mathematics. In the series of revision lectures, we'll do the unit 4 today. We'll discuss a couple of different topics under unit 4 and we'll solve MCQ type questions from unit 4 on groups. As you can recall, we have already discussed binary operations, algebraic systems, groups, subgroups, cyclic groups, cosets, normal subgroups, homomorphisms and symmetric groups in this unit. Today we will do a revision of all these topics in the form of MCQs. Let's do some basic questions first. The first MCQ is on groups again. The set of all real numbers under the usual multiplication is not a group. That's the given statement, and there are 4 possible answers here, one out of which only 1 or 2 may be right. Let's check it out. Option 1 says multiplication is not binary operation. We know that that's not right because binary operation requires 2 operands and multiplication clearly qualifies to be a binary operation. Multiplication is not associative. We have already verified the associative nature, so that cannot be the reason why the set doesn't form a group. The identity element does not exist. Now we know that the multiplicative identity 1 is perfectly a real number that is part of the set, and that's not the reason why this doesn't form a group, which means the last option, it says 0 doesn't have an inverse, and that's what is right. You cannot find a real number x such that 0 times x is 1. Such a number is not present, and therefore there is no multiplicative inverse for 0 which is also counted as a real number, and that is the reason why real numbers do not form a group under the usual multiplication. The second question, we have a different operation given. The set of all integers with the binary operation star, where star is a star b, is a plus b plus 1, is a group. The claim says that this is actually a group, and we are supposed to find the identity element. Now we know that for addition 0 is the identity element, but here even though what is performed is addition, it is not exactly addition. It is a plus b, and to this you add a constant 1. Now we are trying to find the identity element of this group. Now you can obviously verify the other 2 initial conditions. It is closed because you add any 2 integers with 1, the result will also be 1, and addition in general is known to be an associative operation, so that will not trouble you. We are trying to find the identity element. Therefore we are looking for an element E such that A star E and E star A both give us A back. And how do we write A star E? A star E is actually A plus E plus 1. So we are looking for an answer for E such that A plus E gives us A back. And since addition is being performed, I can try and find A by subtracting A on both sides, or let's add minus A to both sides of this equation. Since addition is an operation and the integers form a group under addition, this is 0 plus E plus 1 giving us 0 again. And now to exactly find E, I will add minus 1 to both sides. So 1 and minus 1 will give me 0. So E plus 0 is minus 1. Therefore the identity element this time is not 0 but 1. You can always verify that E star A is going to be E plus A plus 1, and if E is minus 1, minus 1 plus A plus 1 is A again. Therefore A star E and E star A both return the same element A, which means you can call minus 1 as the inverse of the element of the identity, as the identity element of this group. Well, the next one is the same group and the same operation, except over here we are trying to find the inverse element of A. Last time we found the identity element, this time we will try and find the inverse element. And how do we do that? A dash is called as the inverse of A if A star A and A dash star A give us E back, and we just saw that E is minus 1. Now generally A will have its inverse in minus A, but this is not usual addition, so we will have to actually try and find out what A dash can be. And how is the operation star defined? A star is A plus A dash plus 1. The question says A plus A dash should be minus 1, only then you can call A dash as the inverse of A. Therefore A dash, adding minus A on both sides, we have this 0, 0 plus A dash plus 1 is minus A minus 1. Now adding minus 1 on both sides, A dash plus 0 is minus A minus 2, and therefore we see that A dash is actually minus A minus 2. We can also verify if this is right. Let us try A dash star A. A dash is minus A minus 2, and with that I am adding A and a 1, which means these two will give me 0 and these two will give me minus 1, which is the identity element. So option D is the best option which defines the inverse element of A in the given group. And now we have a true or false kind of a question. We have three statements before us and we are trying to find out how many of them are true. The set of all negative numbers forms a group under multiplication. Rational negative numbers. Set of all non-singular matrices forms a group under multiplication. And statement C says set of all matrices forms a group under multiplication. Okay, let us try and solve this now. If you look at statement 1, it says all negative numbers forms a group under multiplication. Negative rational numbers, so any number that is not a square root of 2, square root of 3 types, as long as you can express it as a fraction, you are including them under rational numbers. And negative numbers, in the sense we are looking to the left of 0 on the number line. Now can they form a group under multiplication? Is the set closed? The problem lies in the very first property. The set will not be closed, because when I multiply minus 2 by 5 and minus 1 by 3, both of which are perfectly negative and perfectly rational, their product will be 2 by 15, which is also rational, but this time it is not negative, it is a positive rational number. So the set is not closed. So A cannot be true, A is false. And moreover, when you try and find the associative property, you will see that it satisfies, but the identity element which is plus 1 is not part. So this also does not contain within itself the multiplicative identity 1, that is absent, and that is one more reason why this set will not form a group. And let us look at option C and then go to option B. Option C says set of all, I will just include this extra clause here, set of all matrices of order n, because there is no use in considering one matrix of order 2 by 3 and another matrix of order 5 by 4, you will never be able to multiply them. So let us consider like matrices, similar matrices which have the same order. Set of all matrices of order n forms a group under multiplication. Now you will see that it is closed, you will see that it is associative, you will see that it contains the identity element 1, the identity matrix within itself, but what you will not see that not all matrices will have their own inverse, because I can consider the null matrix with n rows and n columns, and the null matrix will not have its inverse element defined, just like we did not have an inverse for 0, the set of all real numbers. We cannot identify a null matrix, we cannot identify an inverse for the null matrix, and therefore option C is also incorrect, and that is why option B is actually right. Set of all non-singular matrices of the same order, of the order n, actually forms a group under multiplication, because it will remain closed, the operation will be associative, the identity matrix is there, and since the matrices are non-singular, we will be able to identify an inverse for every matrix A of order n. Therefore option C is incorrect, option A is incorrect, only option B is incorrect, only option B is correct, therefore option D is also incorrect. Option D says both B and C are true, we already saw that C is false, therefore only option B is right. Now we have the set of all, we are looking for a false statement here. The set of all rational numbers is an abelian group under addition. Rational numbers is once again all numbers which which don't include the root 2, square root of 3, 4th root of 5, etc. We are not considering the radicals there, anything other than that is okay. Set of all rational numbers under addition. Now we know that addition forms a group for any properly defined set, and set of all rational numbers is one such set, therefore it does form a group, and since the addition operation is commutative, the group is also abelian. So this is actually true, option A is true. Set of all rational integers, there is nothing called as rational integers, set of all integers. Set of all integers is an abelian group under addition. So what works for rational numbers also works for integers, so this is also true. The set of all rational numbers forms an abelian group under multiplication, and that is where we are having a problem, because when you say rational numbers, you are including any number of the form p by q, which means you are also including the number 0, but as we saw before, 0 does not have an inverse. So this third statement here is false, and that is the option we are looking for. Option D is none of them, but that is also false, because option C is the required false statement. And now we have an algebraic system n plus, and if you can recall, the set that is denoted by the letter n is a set of all natural numbers, which means all positive integers starting from 1 and up north. So we are looking at 1, 2, 3, etc. without even 0, and the operation considered here is the very simple operation of addition. Now we are trying to find out what this can be classified into. Can it become a group, a semi group, a monad, an abelian group? Let us have a look at each of them, and let us recall what is also meant by a semi group. A semi group only wants your set to be closed under the operation, and it wants the operation to be associative, both of which is true. When you add two natural numbers, the sum will also be natural. So the set is closed, and as long as you are doing only addition, the operation is also associative. So it is actually a semi group, that is right. Can it become a monoid? A semi group becomes a monoid if it also contains the additive identity, the identity with respect to the operation of addition, and we saw that the set starts only from 1 and starts increasing. So this does not contain the additive identity 0, therefore it cannot be a monoid. If it cannot be a monoid, it cannot be a group. If it cannot be a group, it cannot be an abelian group. So options A, C and D cannot be right, only option B fits the bill. Option A is also wrong because you can't find the additive inverse of any number which is included. The additive inverse of 2 is -2, which is not part of the set, and therefore it can't be a group. If it can't be a group, you cannot call it as an abelian group too. So only option B makes sense, and that is right. Now what about real numbers? We are taking all real numbers and we are trying to classify it. Real numbers, only as long as you are adding, they will always be closed. So the first property is observed. The operation of addition is associative, so the associative nature of the operation is also observed. You can see that it encompasses within itself the additive identity 0. So 0 is a real number, and for every element A there is also an element minus A, which is the additive inverse. So it is a semi group, and because it contains 0 it is a monoid, and since it contains everything else it is also a group, and since the operation of addition is commutative it is also a abelian group. So it is a semi group, it is a monoid, it is a group, in fact it is all the above. All three options are right. That's what we are observing here. Okay. Next up we'll have a look at a few specific groups. The set of all integers modulo 13. Now you can recall that modulo 13 implies we will include every number that can be a remainder when you divide another number by 13, and there are only 13 possible remainders from 0 through 12. So these are the only possible remainders when you divide any integer by 13, and they will be part of this group. The operation involved is plus 13, which means you will add two integers. So a plus 13b will be same as a plus b if the sum is less than 13, and a plus 13b will be a different number, will be the remainder if a plus b grows in excess of 13. Now we are trying to find the inverse of the element 6. Now what will be that number? Let's call it as a. What will be that number which will give me the additive identity 0 when I add it with 6? Now 6 with 1 is 6, 6 with 2 is 8, 6 with 3 is 9, 6 with 4 is 10, 6 with 5 is 11, 6 with 6 is 12, 6 with 7, that is what we are looking for. Remember that 6 and 7 actually give us 13, and when you divide 13 by 13 the remainder is 0. Therefore the inverse is 7. It cannot be 4 because 6 and 4 do not give you 13, 6 and 4 do not give you 0, 6 and 4 give you 10. It can't be 5, 6 and 5 give you 11, which is not 13, which is not 0. 6 and 8 give you 14, 14 is actually 1. Now we are looking for the additive identity which is 0, and that is possible only when you add 7 with 6. So 6 and 7 are inverses of each other, therefore the answer you are looking for is 7. Alright. Next we are considering the relation between a group and its subgroup. A group of order 30 cannot have a subgroup of a specific order. Now recall, this is what we learned under the Lagrange's theorem. If H is a subgroup of G, if H is a subgroup of G, then we saw that the order of H clearly divides the order of G, or in other words the order of G is some multiple of order of H, which means order of H should be a factor of order of G. Order of G given here is 30, and 30 has its factor in 1, 2, 3, 5, 6, 10, 15 and 30. 1 and 30, 2 and 15, 3 and 10, 5 and 6. So any subgroup of the group can only be of these orders. So it can be of order 3, 3 is okay, but you are looking for an order which cannot be possible. So 3 is okay, 10 is okay, 15 is okay, 13 is not okay. Any group of order 30 cannot have an order of 13, because 13 does not divide 30. You divide 30 by 13, you get a remainder of 2, a remainder of 4. It is not a 0, therefore 13 is not a factor of 30. So any subset of 13 elements can never be a subgroup of a group which contains 30 elements, and this is directly as an application of the Lagrange's theorem. Alright. Now the algebraic system 8Z plus is a subgroup of one of these. If you look at the 8Z plus set, we are looking at the multiples of 8 which are like minus 16, minus 8, 0, 8, 16, etc. Now these numbers clearly form a subgroup of Z plus, because they are a subset of Z plus, so they are closed, the operation is associative, they contain they include amongst themselves the additive identity 0, and for every A there is also the minus A, which is the inverse, but we are not looking as a subgroup of Z plus. Can it be a subgroup of any of these? No, it cannot be a subgroup of 3Z plus, because 8Z plus is not a subset of 3Z plus. Now when we defined the subgroup, we saw that a non-empty subset, 8Z plus is not a subset. For example, 8 which belongs to 8Z plus does not belong to 3Z plus, 8 is not a multiple of 3. Similarly, 8 is not a multiple of 5. Similarly, 8 is not a multiple of 16 of 6, but 8 is a multiple of 4. In fact, any multiple of 8 is also a multiple of 4. Therefore, this last option is the one we are looking for. It is perfectly a proper subset of the set of all multiples of 4, because when you write the multiples of 4, you will have minus 20, minus 16, minus 12, minus 8, minus 4, 0, 4, 8, 12, 16, 20, etc. So this set is clearly contained in the 4Z plus, therefore it is a subset. In addition it is closed, in addition it contains the identity, in addition it contains the inverse, in addition the operation is associative, therefore it can only be a subgroup of 4Z plus. Now comparing this to the previous question, we cannot apply the Lagrange's theorem here, because the group that we are considering and the subgroup that we are considering are both infinite order. Now recall that Lagrange's theorem has a restriction that you can apply the theorem only to finite groups. Proceeding further, we are looking at the number of generators of the group Z12 plus 12. You can recall that the term generator is associated with the group which is called as a cyclic group. Any group that is a cyclic group is of such a form that you can express any number, any element using some particular element. We saw that 1 minus 1 I minus I is a cyclic group. It is generated by I or minus I, generated by one of these. It is easily generated by one of these, and therefore the group is cyclic. And the question is, how many generators does this group Z12 plus 12 have? So it goes without saying that the group is actually cyclic, but we are concerned about the number of generators in this group. Can one generate? Of course one generates, because 1 added with 1 itself is 2, 1 gives you 1, gives you 2, gives you 3, 4, 5, 6, 7, 8, 9, 10, 11, also gives you 0. So 1 generates every number when you add those many number of times. Can 2 be a generator? 2 cannot, because 2 will give you 2, 4, 6, 8, 10 and 12, which is 0. 3 can't be, 3 is 3, 6, 9 and 0, 4 is 4, 8 and 0. Now 5, it's an interesting choice, because 5 power 1 is 5, 10, 5 power 3 is 15, when you add 5 3 times it's 15, 15 is 3, 5 added 4 times is 20, 20 is 8, 5 added 5 times is 25 is 1, 5 added 6 times is 30, which is 6, 5 added 7 times is 35, which is 11, 5 added 8 times is 40 and 40 is 4, 5 added 9 is 45, 45 is 9, 5 added 10 times is 50, 50 is 2, 5 added 11 times 55 is 7 and 5 added 12 times 60, which is 0. Now you see that you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12, which is 0. So 5 is a generator, 1 is a generator, 6 can't generate because 6 is 6 and 12 and 0, 8 can't generate. Can 8 generate? No, 8 can't generate, because 8 is 8, 8 and 8 is 16 is 4, 8 and 8 and 8 is 24 is 0. 9 can't generate, because 9 is 9, 18, 18 which is 18 which is 6, 27 which is 3 and 36 which is 0. 10 can't generate because 10 is what happens with 10, because 10 is 10, 10 power 2 is 20 which is 8, 10 power 3 is 30 which is 6, 10 power 4 is 40 which is 4, 10 power 5 is 50 which is 2 and 10 power 6 is 60 which is 0. Now 1 doesn't generate, when 1 generates, 5 generates, what is missing here? 7. Does 7 generate? Yeah. In fact 7 power 1 is 7, 7 power 2 is 14 which is 2, 7 power 3 is 21 which is 9, 7 power 4 is 28, 28 which is 4 again, 7 power 5 is 35 which is 11, 7 power 6 is 42, 42 which is 6, 7 power 7 is 48, 49 which is 1, 7 power 8 is 56, 56 is 8, 7 power 10 is 70 and 70 is 10, 7 power 11 is 77 and 77 is 5, 7 power 12 is 84 which is 0. So 7 also generates, and you can always see that 11 also generates because 11 power 1 is 11, 11 power 2 is 22 which is 10, 11 power 3 is 33 which is 9, 11 power 4 is 44 which is 8, 11 power 5 is 55 which is 7, 66 is 6, 77 is 5, 88 is 4, 99 is 3, 11 power 10 is 110, 110 is 2, 11 power is 121 and that's 0. 11 power 11 is 121 which is 1, 11 power 12 is 0. So 1, 5, 7 and 11, all these numbers generate the entire group, therefore there are 4 generators to this group Z12 under the operation plus 12. So 1 generates, 5 generates, 7 generates and so does 11. These 7 numbers do not generate, they generate only subgroups of the group. Alright. Now we are looking at the set of all even integers under 2z plus is a subgroup, not a subgroup, a normal subgroup, not a normal subgroup of the set of all integers. Now obviously we have already seen this example a lot of times, because when you are adding even numbers you will obviously get even numbers back. So this is in fact closed. Even numbers also contain the additive identity which is 0, and for any number of the form 2a you will also have minus 2a which is an even number again. So it is in fact a subgroup, so option A is right, which means option B is wrong. We have seen that it is a subgroup. Now can it be a normal subgroup? Now recall that we told that a subgroup becomes a normal only when every left coset is also a right coset. Now we may not have enough time to list all cosets of 2z plus, but we can use a property of groups which are abelian. Now we saw that if G is abelian, if G star is abelian, any subgroup is also a normal subgroup. Any subgroup H is also a normal subgroup. So you don't even have to verify the left and right cosets to be identical or not, you can directly see that they will be identical and therefore it is also a normal subgroup. So obviously option D is also incorrect. Alright, a non-empty subset H of a group G star gets called as a subgroup if dash and dash properties are satisfied. We learned this under the heading of the 2 condition test. As long as you have a non-empty subset of a group, you can show that it is a subgroup if you can verify only for the closure and the inverse property. If only these 2 properties are met, it will obviously mean that the subset actually forms a subgroup. Therefore option C is what we are looking for, because option A does not talk about the inverse, it can't be right. Option B does not talk about closure, it can't be right, and option C is what we learnt under the 2 condition test, and that is perfectly right. Therefore none of the above is also not correct. So one condition that you will have to look out for is the closure property, the other one is the inverse property. There is an inverse for every element any non-empty subset which is also closed will easily become a subgroup. Okay? A non-empty subset H of a finite group G star becomes a subgroup of G star if whatever is satisfied. We also learned this as a follow-up of what you call as the one condition test. The one condition test, I recall, it says that whenever A star B inverse belongs to H, H is a subgroup, but that is in general, that is not about finite groups. Here there is a restriction on your choice of G star which has to be finite. Now if the group is finite, it is enough if you check for the closure property, because as long as the group is closed, you will be able to easily identify some element as the inverse of any given element. You do not have to check for the inverse, you do not have to check for the identity. As long as the closure property is identified, you will see that the non-empty set will actually form a subgroup of the given finite G star. And for the last question on this unit 4, let us do a revision of how to do an operation between two permutations. And as long as you are familiar with this, you can do any other problem on permutations. This is two elements from the symmetry group S8. Now S8 will have 8 factorial elements, and 8 factorial is of the order of 40,000. So you cannot list all elements and find out what the inverse is. Let us find out if one of these answers is right. And how do we do that? Now the convention that we agreed was to move from the left to the right. You will follow the images, and as in 1 is mapped to 5, but 5 is mapped to 7. So 1 is mapped to 7, 2 is mapped to 4, but 4 is mapped to 3. So 2 goes to 3, 3 goes to 6, and 6 goes to 5. So 3 goes to 5, 4 goes to 7, and 7 goes to 1. So 4 goes to 1, 5 to 2 and 2 to 8. So 5 to 8, 6 to 3 and 3 to 2. So 6 to 2, 7 to 1 and 1 to 4. So 7 to 4. The last one 8 to 8 and 8 to 6. So 8 to 6. So this is the result of the binary operation on these two elements from S8. Now where do they match? We are looking for a sequence 7 3 5 1 8 2 4 6. So this is 7 8, so this can't be right because looking at 7 3, this also can't be right, and 7 3 5 1 5 1 8 is what we want, because 5 to 2 and 2 to 8. So 5 8 is what we want, so B is also not right. It has to be A. 7 3 5 1 8 2 4 6, and that is option A. So that is how you do permutations. If you want, we can also find the inverse of this element. To find the inverse, we saw give you an easy, let us call it A, and to find A dash, what we will do is we will write the images first and then flip them. So writing the images is 5 4 6 7 2 3 1 8. Let us write down what we have: 1 2 3 4 5 6 7 8, and let us just write them in the usual sequence: 1 7 2 5 3 6 4 2 5 1 6 3 7 4 and 8 8. This will be the required inverse: 1 to 5 and 5 to 1, 2 to 4 and 4 to 2, 3 to 6 and 6 to 3, 4 to 7 and 7 to 4, 5 to 2 to 5, 6 to 3 to 6, 7 to 1 to 7, 8 to 8 to 8. So this is the inverse. So this is also how you find the inverse of any permutation, and that should be enough for you to have a recall of what we learnt under symmetric groups and permutations. Now with that, we will wrap up this revision session on the 4th unit on groups. Thank you.